Let us discuss one more example on 3D space frame structure in lecture 27 module 1 of computer methods of structural analysis applied to offshore structures. In this example, we will take up slightly a different problem and try to solve this using computer codes again. I will also give you the computer code in parallel and show you the results as obtained from the output of the computer program directly, then compare the results at the end moments of the frame and check for its equilibrium conditions for the applied loads. This is my structural system which I am marking now. Subjected to a load on this member, which is about 20 kilonewton per meter. Let us mark the dimensions of these. Say this is 4 meters, and this is 3 meters, and this is 6 meters. Let us say EIY is same as EIZ is same as simply EI, and the torsional constant GIX is 1/4 of EI, and the axial rigidity constant AX is 1/4 of EI. So, let us say these constants are available to us in this form. We want to analyze this. Let us mark first the local axis and global axis of this frame. Let us mark the nodal points A, B, C, D, E and F. So, for the member AB, the local axes are XM, YM, YM and ZM. For the member BC, XM, YM and ZM. For the member DE, XM, YM and ZM. For the member EF, XM, YM and ZM. For the member EB, XM, anticlockwise YM and ZM. Okay. Then the global axis is taken the origin here, x axis, y axis and z axis. Okay. Having said this, we can quickly make a table of coordinate systems to understand the joints. Let us make a table joint and what are the x, y, z coordinates of each joint. Let us say A, B, C, D and E and F. Okay. The dimensions are available on the screen now. This is my origin, therefore, A will have x as 0, y as plus 6 and z as 0. B will have A as plus 4 meters, plus 6 meters and 0. C will have x as plus 7 meters, plus 6 meters and 0. D of course is located at the origin of x, y, z. E will have plus 4 meters and y and z will be 0 and F will have plus 7 meters and 0. So, this is a very interesting input which you require from a computer program. So, I am saving this as it is. Let us now prepare a table of direction cosines and the psi y angle, this table 2. Let us say for the member, each member we need to know the length of the member, we need to know where the j and k joints of the member are placed and the direction cosines, namely Cx, Cy and Cz. Then what is the kind of transformation we are recommending, then what is my psi angle. Okay. Let us make a table. So, there are members AB, BC, DE, EF and EB. There are 5 members. Okay. AB, BC, DE, EF and EB, 5 members are there. Length of each member is known. So, let us enter these length 4, 3, 4, 3 and 6 meters. Okay. J and k ends of the members are now marked. So, AB, okay. This is BC, this is DE, this is EF, this is EB. Okay. Now, what is the direction cosine? It is the angle of xm with x, okay, xm with x, xm with x. You know this is going to be 0. So, if a cos 0 is 1 and obviously with y and z it will make 90 degree. So, this is going to be 0. This is true for all the remaining 4 members as well, but for the 5th member, if you look at xm, xm is making 90 degree with x. Okay. So, cos 90. So, I should say this is 0 and xm is making 0 degree with y, therefore, cos 0 should be 1 and 0. Now, if you look at the member AB or BC, DE or EF, xm is aligned with x global. I can recommend any transformation. Let us recommend y zx transformation for all these 4 members. So, I will get psi y and for the 5th member, you know, x is oriented with y, therefore, I cannot make y zx, I should recommend z yx transformation, I will get psi z by inspection. Okay. Now, what is the angle of psi y? It is actually ym with y. Let us say what is ym with y? It is 0 degree because ym and y are aligned. Therefore, this is going to be 0 for all these 4 members. In this case, it is yz with y, let us say. Okay. So, let us talk about ym with y for the 5th member. So, for the 5th member ym is vertical and y is this way. So, 90 degree. So, I should say this value is going to be 90 degree. So, there is no difficulty and we need to save this information for the computer program. Having said this, let us now estimate the C matrix for each member. So, C matrix actually will have C I j, I will represent the inclination or representation of x m axis, and this will represent inclination of respective x, y and z axis with x m. Okay. So, let us go for C A B. So, it is going to be a 3 by 3 matrix, we know that. Okay. Let us see what is the inclination of x m with x. So, it is 0. Okay. So, therefore, and y m with y and z m. So, x m with x is 0, x m with y is 90, x m with z is 90. Therefore, it is going to be 1 0 0, right. Similarly, y m with x is 0, so 90, y m with y is 0 and y m with z is 90. So, the cosine angles of them respectively will be 0 1 0. Similarly, if you look at the z m axis makes 90 degree with x and y global, but z m makes 0 with z. Therefore, the cosine values of them will be 0 0 1. And obviously, from inspection you know the C matrix for the member A B, B C, D E and E F all will be same. So, I can write this as equal to. So, C matrix of A B will be as same as B C, D E and E F. Okay. Let us do it for C E B, that is the fifth member. Okay. So, what is the fifth member is located here, this is my fifth member. Okay. X m makes 90 degree with x, okay. X m makes plus 0 degree with y and x m makes 90 degree with z. Therefore, I should get 0 plus 1 0, is it not? Similarly, let us see y m is make 90 degree with x, 90 degree with y, but it is plus with z. So, I should get cos of these angles should be this one. Similarly, if you look at the z m axis, it makes plus with x and with y and z is 90. Therefore, I should say plus 1 0 0. Now, I have got the C matrix for all members 5 members here. So, this will be also a required input for my problem. Okay. So, then based on the transformation applied and based upon the member stiffness matrix, I can always find the local member stiffness matrix and global member stiffness matrix by following the same procedure what we had in the last lecture for the last example 1. Let us now quickly work out the load vector. So, this is my beam member, that is E B, okay, E B. So, applied by a uniform distributed load, okay, of 20 kilonewton per meter for a span of 6 meters, is it not? So, you can see here for a span of 6 meters the load is applied. So, I want to work out the joint load. Okay. So, let us try to work out the joint load for this. So, I would like to see what would be the effect of these loads. Okay. So, I am marking the axis, global axis. Okay. So, you know the global axis are x, y and z. So, this is x global and z global and this is going to be y, is it not? X, y and z. So, if I apply a moment, I will get this value is going to be 20 into W L square by 12, okay, which will make it as 60 kilonewton meter, and in this way this will be 60 clockwise. Now, the reactions, this will be 20 into 6 by 2, which is again 60, and this reaction is also going to be 60. This may positive x, positive z and positive y, positive z, positive y and positive x. Okay. I can now make the joint load vector for the member E B local, which will be along x 0, okay, along y 0, along z. I am making a fixed end moment value. This is the fixed end moment of the local, okay, of the member E B. So, this is going to be plus 60. Okay. Similarly, the next case 0 0, then minus 60, so plus 60, 0 0 and so on. Okay. So, let us now mark the degrees of freedom for this problem. So, that let us have the labels of this. Let us mark the unrestrained degrees of freedom. So, at this joint along x delta 1, that is delta bar 1, delta bar 2, that is this x y z, this is my capital X, this is my capital Y, this is my capital Z. Okay. So, I have to mark the degrees of freedom according to this style. So, delta bar 1 along Y and along Z. Okay. Then the moments. So, I should say theta bar 4, theta bar 5 and theta bar 6. Okay. So, 6 degrees of freedom here. Then let us come to this joint delta 7, delta 8 and delta 9. I am putting bar because they are global displacements. Okay. Then rotation, (11) and 12. Let us now mark the unrestrained degrees of freedom. Let us say 13, 14 and 15, 16, 17, 18, then 19, 20, 21, 22, 23, 24, then 25, 26, 27, 28, 29, 30, then 31, 32, 33, 34, 35, 36. So, there are unrestrained degrees of freedom, which is varying from labels of 1 through 12, and restrained degrees the labels are varying from 13 till 36. Okay. There are 6 joints, total 36 degrees of freedom, out of which 12 are unrestrained, remaining all are restrained degrees of freedom. So, now having understood this, let us mark the labels. The labels of the member E B, because this is A, this is B, this is C, D, E and F. So, we are looking for this member because this member is actually loaded, is it not? So, that is what we have here. So, now let us enter the labels of this very easily. I know you will be able to relate these labels very easily with respect to what we have here in the member E and member B with respect to global axis. Okay. So, the joint load vector is just reversal of this. The joint load vector, if you want to make the joint load vector, which will have 36 into 1, which will be, let us see for example, the global degrees of freedom. Along 1 there is no force, okay. Along 2 there is no force, along 3 there is a force which you get from here, but that is reversed, okay, because these degrees of freedom can be marked very easily, okay. These degrees of freedom can be easily marked. So, along 3 there is an upward force, but joint load vector will have reverse. So, let us reverse that. So, by this logic 0 0 minus 60 plus 60, okay, 0 0 0 0, then minus 60 0 0, remaining all will be 0. So, it is going to be 36 by 1. I have entered the unrestrained degree loads, okay. Remaining all, there are no loads here, okay. That is the matrix we have. Let us solve this problem.